Today we're going to take a look at the mathematical background needed for the simplex algorithm. So there will be some geometry, some algebra. Let's take a look at a linear program. So here we have a linear program, we have our objective function, we have our linear constraints. So let's compare this to something that actually looks quite similar, and that is linear algebra. So in linear algebra, we commonly want to solve a set of linear equations or a system of linear equations. Linear programming very similarly, just that we commonly have linear inequalities. Now the most common algorithm for linear algebra is a Gaussian elimination. In linear programming, that's the simplex method. And finally, the solution space in linear algebra actually is quite simple. It is an affine subspace. So affine subspace means essentially we have a vector space with possibly a translation. So for instance, in 2D, a line, that's an affine subspace of the two-dimensional plane. In linear programming, this is quite different. Here, our solution space, so the set of feasible solutions, is a convex polyhedron, and we will be looking at convex polyhedra in a moment a bit more, but for now, just think of a convex shape as we already saw in the example that we had. And this is more complex than an affine subspace, which makes linear programming as such more difficult. So the solution space can be more complex. What will rescue us is the following. So we also have our objective function. So we don't actually want to compute the whole solution space, but we only need to compute one optimal solution. So if we can avoid computing the solution space, then we can avoid the complexity, at least to some extent, that comes from that. So now let's talk about convex polyhedra or convex polytopes. This is again linear program. We have this shape. This is obviously convex. So what does convex actually mean? Convex means that for any 2 points in that space, the line segment between them is also within that shape. So we have this x here, which is in my case it's blue area, and it is convex because any 2 xy, the line segment is also included in x. You could also say x and y see each other within x. So that is convexity. In our setting, y is a solution space for a linear program convex. In linear programming, each of the constraints, so let's say we have a linear inequality, gives us a half space. And we get here a half space. And a half space as such is convex. And the intersection of convex sets, and we get an intersection of half spaces here, is again convex. So that's why we know that our solution space is convex. And a convex polyhedron can be simply defined as intersection of finitely many closed half spaces. So what we have here is exactly a convex polyhedron. I should say convex polyhedra, they do not need to be bounded. If they're bounded, we call them convex polytopes. So even if, let's say, these 2 constraints weren't there, and we would have a solution space going to infinity here, also that counts as a convex polyhedron. We want to take another perspective on convex polytopes. And for that, we come from a different direction, and we're going to look at the concept of a convex hull. So if we have a subset of the space, then, and that is x here, in my case, x are all of these points, then the intersection of all convex sets containing x is called the convex hull. So this will look like this. So the blue area here is the intersection of all convex sets that contain all of those black points. And now we are ready to define a convex polytope, and actually we will have 2 definitions. So one is a convex polytope is a bounded convex polyhedron. So bounded intuitively simply means it does not go to infinity, or if we want to define it, we can say it stays within some ball. And so that's one definition. The other one is a convex polytope is a convex hull of a finite set of points. And then there's a Minkowski-Weil theorem, which tells us that definition 1 and 2 are the same. So we can see convex polytopes as intersection of half spaces and then bounded, or as the convex hull of a finite set of points, and this is actually the same. And in our example here, we can either see this blue area as the intersection of the half spaces, as we actually get it because the linear program states it gives us a space like that, but we can also see it as the smallest convex set containing all of those corners. Assuming that we can find the solution to our linear program by simply looking at the corners of this convex polytope, a natural question is to ask, given the half spaces, can we easily find those vertices? Because if we could simply go through those and find the optimal one. And vice versa, you can also ask, given the vertices, is it easy to find the half spaces? And the answer to this is no. And to explain this at least complexity-wise, we're going to look at specific polytopes, and those are cubes and the dual cross-polytope. So a cube is what you'd expect it to be. So here we have cubes in 1 up to 3 dimension. Let's look at this cube. So this is the cube. So here's my 0, and then I have 1, the 1, 1, and 1 here, and I'm looking at this space over here. So how could I define this cube as an intersection of half spaces? So that's actually easy, because we just have to take the half space for each of the coordinates. We're going to say xi should be larger equal 0 and xi should be smaller equal 1. Yeah, so those are the half spaces. If I do that for all I, for each of the dimensions, then this gives me a cube, or more specifically this cube. Now, what are the vertices? Any 0, 1 vector, let's assume we're looking at a 5-dimensional cube here, is a corner of the cube. So in my 3-dimensional example, I have triples, so I have 0, 0 down here, 0, 0, 0. Here I have, let's say this is coordinate 1, so it would be 1, 0, 0, and so on. So how many half spaces do I need to define this cube? For each dimension, 2. So I have, if n is my dimension, 2n half spaces. How many corners do I have? I can get any vector here of length n with 0 or 1. So for any position, I have the choice of 2. So this is 2 to the n. Yeah, so I have, in general, 2 to the n vertices and 2n faces. What you can already see here now is that even if I only have a linear number of constraints, I would get an exponential number of vertices. So going through all vertices is too expensive. One more curiosity to point out. So in 4D, what I'm showing here is a so-called Schlegel diagram. So if you haven't seen that yet, that's an interesting construction to show 4-dimensional polytopes. But now let's move on to cross-polytopes. What is a cross-polytope? We want to have that the sum of the absolute values of the coordinates is at most 1. So how many vertices do we have? So the vertices all have the form. I essentially have a vector of zeros. Just on one position I have a 1, or actually a -1. So for every coordinate, I get 2 vectors. So we have 2n vertices. In terms of the number of faces, so here, I mean, this is a nicely compact way of writing with this, with absolute values. But I have to, in terms of the linear inequalities that this generates, I essentially need to combine all kinds of versions of combining positive and negative, so maybe x1 minus x2 plus x3 and so on. That has to be smaller or equal to 1 and so on. So this gives me actually 2 to the n combinations. So we have 2n vertices and 2 to the n faces. So also in the direction, if I have a linear number of vertices might imply an exponential number of faces. So what we see by this example, that it's definitely not easy to go from vertices to faces or faces to vertices, because in this situation from a linear number of vertices we might get an exponential number of faces, and likewise from a linear number of faces we could get an exponential number of vertices. This is what I wanted to say about polytopes. Now let's take a look at the equational form for linear programs. And before doing so, let's first look at some non-equational forms once more. We already know that any linear program can be written in this form here, where we are maximizing our objective function, and we're using now vector and matrix notation. So we have the C transposed X, and then subject to AX smaller equal B. So A is an M times N matrix, B an M dimensional vector. And what will be important in the following to remember: N is always a number of variables, M is always a number of constraints. Now, if we have a linear program in a different form, and for instance this form here where we want to minimize our objective function, and we do not necessarily have smaller equal here, but larger equal ones and equality. So how can we rewrite it in the form with maximum and then the matrix form that we've seen? So first of all, instead of minimizing this function, if we multiply this with -1, then that function we want to maximize. Yeah? So this is easy. Instead of minimize, we get maximize the negative. And now we need to rewrite the constraints. So if there's a larger equal there, we can multiply with -1 and it becomes a smaller equal. If we have equality, we can simply write this as two constraints: smaller equal, larger equal. And then of course the larger equal we again want to get rid of, so we multiply it with -1. So that is what we get. Here's the smaller equal, and this is the larger equal, but then multiplied with -1. And then if we've done all of this, we again have this form that we wanted to get, where we have a C vector, -3, -4. Okay, we have x1, x2, the A we can read off here, and the B we can read off here. Now let's get to equational form. So the equational form for a linear program is as follows. We want to maximize C transpose X, so this is as before, but now all of our constraints, and that's why it's called equational form, so it's often also called standard form, but we will call it equational form because we have an equations here. So we want the constraints we write as AX equals B, and additionally all of the variables need to be non-negative. And now we want to see that we can rewrite linear programs into this form. Let's take this one as an example. So we have maximized something, so that's perfect. But now there's a smaller equal here. So to bring this into equational form, we are going to introduce something that is called a slack variable. The slack variable is just a new variable that we add, like this, where starting with a smaller equal, we simply add a plus x3 here. And since x3 should be larger equal 0, these two lines are equivalent. So this is smaller equal if there is an x3 such that this is equal. We can do the same here for the second line. There, of course, we have to be a bit careful because now that's not smaller equal, it's larger equal. So what we would do first would be to multiply with -1. So then we have also again a smaller equal, and then we add our slack variable x4. So what we have right now is the following. Now we want to maximize our objective function subject 2, and then we have these two equations. So this is exactly what we want to have, except that we want to have all of the variables being positive, and right now x1 is not yet constrained to be non-negative. So how can we add this constraint while still allowing that our original x1 could be actually negative? So we rewrite x1 as x1 prime minus x1 double prime. Both of those should be non-negative. So we're going to replace x1 by those two variables, and in effect what we get is that, so if x1 should be positive, we simply get this by having x1 prime positive, but we can also make x1 negative by simply making x1 double prime positive. And now the linear program looks as follows. We replace x1 by this here. So also in the objective function, we now have 3x1 prime minus 3x1 double prime plus 4x2. And then also down here, you see how we replaced x1. And now the linear program is in equational form. The only thing that we might now still want to do is rename all of this. We just relabel the variables so that we really have here x1 up to x5. Any linear program we can bring into equational form, and also the complexity does not increase significantly. So if we previously had n variables and m constraints, then we have at most m plus and then 2n variables, and the number of constraints does not increase, so we still have m constraints or equations. In the following, so in this video and also when we do the simplex algorithm, we are going to assume that the linear program is given in equational form, and we will make two more assumptions, and those are the following. We assume that the system of linear equations has indeed at least one solution, and we're going to assume that the rows of A are linearly independent. So if that wouldn't hold, then we would have the following. So if there's no solution, then we directly know that the linear program itself is infeasible. And if the rows are not independent, then we can simply get rid of some of the rows without losing any information or without changing the solution. And how can we determine that these conditions hold? So there we can simply use linear algebra. So this would mean we want to do Gaussian elimination. Now that we know what equational form is, we're ready to look at so-called basic feasible solutions. Before I define and analyze those further, let me first give you some intuition. So we are trying to find the optimal solution to our linear program. And the idea here is that the optimal solution has to be a corner. So in this picture here, in this figure, so my affine subspace is some kind of blue plane. So a two-dimensional plane in three-dimensional space, but I'm taking my LP, because all of the coordinates have to be non-negative, my LP takes now this subspace and cuts it with a positive octant, and this gives me this triangle here. And a solution to the LP, an optimal solution to the LP, now should be one of those corners here, and which one depends on the LP. So for instance, if my linear objective function, if the orthogonal to that is this red plane here, and let's say the max is attained by pushing this as far right as possible, then the optimal solution would be R. And it has to be a corner because Q, something on an edge here, will never be extreme with such a plane. Likewise, any point inside. The only exception is if the plane is, for instance, collinear with the edge here, but then still, even as Q would be optimal, then R would also be optimal. So it is sufficient to look at corners. And now we want to take a closer look at properties of those corners. And there we can make the following observation. So we have our affine subspace, in this case a two-dimensional space, and it's two-dimensional because it's we overall have a three-dimensional space. It's defined by one equation in this case, and this gives us a two-dimensional space. Now to get a corner from this, so the corners must lie on the sides of the octants. So cutting with the side of an octant, so let's call this x3, and here this is the x3 equals 0 plane. Cutting the subspace with this plane gives me this, actually this line here. Yeah, so by cutting with a plane, I reduce the dimension of the space I'm considering by 1. I started with a two-dimensional subspace. I cut with one side, that gives me a one-dimensional space, but a corner is zero-dimensional. I mean, a point is zero-dimensional. So it's clear that I would have to cut with yet another plane. So this would be, if this is x2, this would be the x2 equals 0 plane to actually get a corner. But what that means is that the solution I'm interested in here, R for instance, has two of the coordinates being 0, because cutting with this plane is says we're setting x2 and then we're cutting with the other plane and x3 to 0. So that's the intuition here. If we start, if we have m equations, then the affine subspace we're looking at is n minus m dimensional. Now the solution space is this n minus m dimensional space, and then intersected with a positive octant. And to get a corner, we will have to intersect the affine space with n minus m of the sides of this positive octant, which means that we have at least n minus m coordinates that are actually 0, or stated differently, all coordinates except for m are 0. So in my example here, for a corner, at most one of the coordinates is non-zero. And this is in the setting again where we have m constraints and n variables. So this idea is formalized by the concept of basic feasible solutions. So what is a basic feasible solution? We are looking at feasible solutions. So we have n variables, so they live in R to the n. And a solution is basic if there is an m element set, so subset of 1 to n, such that if we consider the square matrix AB, and AB is a matrix that we obtain by taking the columns of A corresponding to B. So this square matrix should be non-singular, or stated differently, full rank, or stated differently, the columns or rows should be independent. So that's also what I'm saying here. The columns indexed by B are independent. So B should be chosen such that AB is non-singular. And now getting back to the solution that we're looking at should be 0 for all of the indices that are not in B. Okay, so let's take a look at an example. If this is A, and I set B to be 2, 4, I'm looking at the second and the fourth column. Those are linear independent. And if I look at a possible solution, x, I get the solution. So for ax, a times x equals b, I get the solution x being 0, 2, 0, 1, 0 by setting the other coordinates to 0 and then solving the rest. And because this is non-singular, I get a solution, and this solution in this case is I get positive values. So it is actually a feasible solution. So 2 times 5, 1 plus 1 times 4, 5 gives me, so 2 times 5 plus 4 is 14. 2 times 1 is 2 plus 5 is 7. Yeah, so this solves this set of equations. It fulfills the condition that it's 0 for all of the variables which are not in B, and here for B, those two columns are linear independent. And this is now a basic feasible solution. So let's look at a few more examples. So let's say this is A, this is B. Then we should know that this, first of all, X is a feasible solution. You can easily check this. So A times X is simply 10, 2, which is exactly B. So it is a feasible solution. So it's a basic feasible solution, but it's a basic feasible solution for various choices of B, namely all of these choices, as long as the second column is included, and as long as the other column and the second column are together give me independent rows. Yeah, so what we see here is that a basic feasible solution might be the basic feasible solution for several bases. But the other way around, for any basis, there is at most one basic feasible solution. And the reason being, if you fixed your basis, then you set all of the other variables to 0. You have those two that are non-zero, and the columns are independent. There is exactly one solution, which you can also see by the fact that because AB has full rank, you can get the solution also by inverting AB and then multiplying B with that, and this gives you a unique solution. Yeah, so any basis determines at most one basic feasible solution, but a basic feasible solution can belong to several bases. One more example. So if you look at this A and this B, try to figure out whether 3, 4 gives us a basic feasible solution. But first you might think yes, because if you look at those two columns, they are linear independent. But now if you solve this system, so if you want to solve 10, 2, which is B equals AX, and you write this with just using x3 and x4, and then you get these inequalities, you can solve them, you get a unique solution, and this is your unique solution, and you see that x4 is negative. So while the set of linear inequalities can be solved, you do not get a feasible solution because everything has to be non-negative to be feasible. How about 3, 5? Do we get a basic feasible solution if we take this basis? No, because this is not even a basis, because those two columns are linear dependent. So when I introduced basic feasible solutions, I already said that we're interested in them because they correspond to corners, and because this also means that the optimal solution will be a basic feasible solution. So let's put this into a theorem. So this theorem states that if there is an optimal solution for our linear program, then there is a basic feasible solution that is optimal. And one way to see it simply is when we consider the simplex algorithm, then from the proof of correctness of the simplex algorithm, because the simplex algorithm works on basic feasible solutions, this will also already imply the theorem. Another way to see this is that to show that each of the vertices of the feasible region corresponds to basic feasible solutions. We will not want to do this proof here. It is in the book if you're interested in, so in the book by Gärtner and Matuszek. Now, with this knowledge, we already could find the optimal solution by simply looking at all basic feasible solutions. So this would be a very simple algorithm. Simply find all of the basic feasible solutions, go through all possible bases, check whether there is a corresponding basic feasible solution, look at which one is optimal. The problem being that there are too many of potential solutions that we have to go through. So this will be a too large number. This doesn't really make sense. So we need to go through the basic feasible solutions in a clever way, and we're going to see in the next videos where we discuss the simplex algorithm that the simplex algorithm exactly does this. Now let's bring together basic feasible solutions and the vertices of the convex polyhedron that results from our linear program. I put all of the definitions here once more. So what is a basic feasible solution? Then also the observation that for every basis we get at most one basic feasible solution, and the observation that if we have an optimal solution, then we also have an optimal basic feasible solution. When defining basic feasible solutions, we did not yet use the objective function, so C transposed X. We're going to take a look at the objective function, and first of all the perspective on convex polyhedra, namely the corners of a convex polyhedron, or the vertices. So X is a vertex of a convex polyhedron if and only if, or here I'm giving this as a definition, if there is a C such that C transposed X is maximal and X is also unique with this property. So you could see as saying there is an objective, linear objective function which has this point X, or this vertex X, as unique solution, then it is a vertex. And in this example here, if we have this cube here, you see this plane, so the C orthogonal to that plane, but the plane demonstrates that this corner here V is a unique optimum in relation to this objective function, or in relation to this linear equation. So this is a way to define the vertices of a convex polyhedron, and with this definition we can prove the following theorem, namely that if we have a linear program in equational form, then the vertices of the feasible region correspond exactly to the basic feasible solutions. So this is what I already tried to illustrate when I introduced the concept of basic feasible solutions. Now we're ready to prove that. The fact that the vertex is also a basic feasible solution follows now already from this theorem 423, which said that if there's an optimum, then there's also an optimum basic feasible solution. But we know that we can define a vertex by a C, and having that vertex as the optimum, the unique optimum for that C, and this means that this vertex already has to be also a basic feasible solution. Now let's do the other direction. So if I have a basic feasible solution, I want to show that it is also a vertex, and we do it as follows. So now we have to define a suitable C such that this basic feasible solution is the unique solution if we take C transposed X and maximize it. Now we can define C as follows. We simply set it to 0 for all of the indices of the bases and -1 otherwise. Intuition being, my basic feasible solution has a property that it's 0 for all of the indices not in the basis. So this -1 does not affect my basic feasible solution. It will simply end up with 0. And it is non-zero for those indices, or can be non-zero for the indices corresponding to the bases. But that doesn't matter, because then I would be multiplying with 0. So that means that for the basic feasible solution for the spaces, I get that C transpose X is actually 0. And since the basic feasible solution is unique given the basis, any other solution will not be 0 on all of those, and therefore will have a value smaller, and therefore X is indeed a vertex of our polyhedron. So what have we seen? we've seen that the set of feasible solutions to our LP is a convex polyhedron. We've seen how to write LPs in equational form. Then we had this concept of basic feasible solutions, which we looked at extensively, and then finally observed that the vertices of a polyhedron exactly correspond to those basic feasible solutions. And with all of this in place, next we're going to take a look at the simplex algorithm, which makes use of basic feasible solutions and finds the optimal basic feasible solution in a clever way.